Okay, good morning. Are you hearing me well? Okay. Okay. I'm sorry for this delay. So I'm going to start this session and this conference addressing a few words. Just okay. Good morning, everyone. I greet the president of the Knowledge Hub of Universities, Dr. Yasser Sakr, our vice rector, Professor Amar de Matos, the mentor of this idea and project. I also greet Ihab Salama, the CEO of Elsewhere Education, and Mariam Dras, CBDO of Elsewhere Education, our constant and consistent supportive friends. The program directors of NOVA and our faculty, Dr. Ebtisam, she is always supporting us and esteemed colleagues. Marcello Pelillo is a professor of computer science at the University of Venice, Italy, where he directs the European Center for Living Technology and leads the Computer Vision and Pattern Recognition Group, which he founded in 1995. He held visiting research positions at Yale University, McGill University, Canada, the University of Vienna, York University at UK, the University College London, and the National ICT Australia also. His research interests correspond to areas of pattern recognition, computer vision, and machine learning. At present, he is particularly interested in similarity-based pattern recognition methods, in graphic theoretic models, with an emphasis on continuous-based approaches and in the interplay between game theory, pattern recognition, and machine learning. Problems he is currently working on are data clustering, semi-supervised learning, structural matching, contextual pattern recognition and labeling problems, image/video segmentation, perceptual grouping, shape representation, and recognition. So envisaging AI as a potential application for archaeology is related with ways offering tools and methodologies that can transform our archaeological research, the way it's conducted, data is analyzed, and insights are gleaned. There are several areas: predictive analysis for site discovering, artifacts analysis and classification, 3D reconstruction and visualization, and monitoring and preservation, and so many others. NOVA is under the umbrella of the Knowledge Hub of Universities and is an international branch campus committed to teaching quality, offering in Egypt the same degree being offered at the parent university. We are fully committed to the law number 162 of 2018, issued by the presidential decree, and mirroring teaching quality and the high standards of quality control. Being part of EUTOPIA, an European alliance of universities, we are not alone on this endeavor, and we believe that there is no teaching quality without research excellence. Nova Cairo EUTOPIA talks fulfill this purpose. With the permission of our president, I will give the floor now to our esteemed guest speaker. Thank you, Marcello.
Thank you very much. Thanks, Francisco, for this nice presentation, and thanks for inviting me here. It's really a great pleasure to be here. This is my first time in Egypt. Okay. So yeah, once again, good morning, everyone. It's really a great pleasure for me to be here. Hello to everyone from home. So today, as you know, we will be talking about applications of AI in archaeology. And in particular, I will be talking about a research project that I'm coordinating, a European project, which is called REPAIR, which basically will allow us to physically reconstruct large shattered frescoes. And we are doing this by the latest technologies in artificial intelligence and computer vision and machine learning. The talk today, by the way, since I've been told that there's a kind of mixed audience, so maybe not many of you are familiar with AI and with the basic ideas behind artificial intelligence and machine learning. In this presentation, I will be first talking about First talking about. I will try to give a very super short introduction to AI, basic ideas behind AI, the basic philosophy also behind AI, and then we will move on and try to describe what we are doing in this REPAIR project. So first of all, I'd like to put things into historical context. Let's see, I'm not sure how. Okay, here we go. So in the first place, AI has a long history, of course, not as long as, say, physics or biology or whatever. The conventional year of birth of AI is traditionally set in 1956, but we have to be careful about these dates because actually before that date, a few people around the world, even during the Second World War, they were already working on ideas that we are using nowadays. Actually, one of the very first papers that was published in this very broad area was published in 1943. And in that paper, we already found things that we use nowadays. In that paper, which was written during the Second World War, actually, we find the first formulation of a formal neuron. And probably, as you know, nowadays, if AI is becoming so powerful, it's because of the success of the neural networks. And neural networks are large networks of artificial neurons. Well, actually, there are those, and I'm included in that group, who think that the conceptual foundations of AI go well back in history. There are people who think, for example, that philosophers like Leibniz can be considered also in some sense, of course, the fathers, or among the fathers of AI, because he was among the first to show the importance of logic in reasoning and stuff like that, things that we do, of course, normally in artificial intelligence. By the way, going back to our 1956 event, why is considered so important for AI? Because in that year, there was a workshop in the United States at Dartmouth College. You can see a picture here of some of the fathers of AI, among whom you can see Marvin Minsky, Claude Shannon, who basically set the stage for what we're doing today. So what happened is the following thing. John McCarthy, one of the fathers of AI, wanted to organize a workshop, a 2-month workshop in the Dartmouth College in the United States, trying to gathering people working in AI at the time. And although the area was not really known as AI, and he submitted a proposal to the US government asking for money. Of course, when you run these kind of workshops, you need money. And in the proposal, which was written in 1956, you already find the first occurrence of the word artificial intelligence. You can see here that we proposed a 2-month, 10-month study of artificial intelligence be carried out in the summer of 1956 at Dartmouth College in Hanover. And then you can find here a sentence which can be seen as the agenda for the whole field. The study, he says, is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that the machine can be made to simulate. This sentence you can find already in the proposal, which of course got accepted, and so the workshop actually took place, is in some sense the agenda or the main goal of artificial intelligence. And we have to distinguish, we need some clarifications, because sometimes, especially nowadays that AI is so popular, and each and every day you can listen on the news, new fantastic achievements of AI, it's important to make some distinctions. First of all, AI is a very broad field, and the objective of which we already see is the idea that we can build a machine or an algorithm that is able to simulate the activities done by our brain, basically, our cognitive capacities. This is a very broad area, which includes several things, including machine learning. Machine learning is a subfield of AI. Actually, for many years, machine learning was not so important in the field of AI, in the sense that people believed more in logical reasoning, believed more in things that have nothing to do with machine learning. And for many years, machine learning was considered kind of a very small and not really so important area within the AI field. So first distinction, yeah, please.
Sense.
Perception, to perceive the world. Okay. Yeah, sensory, image, to elaborate and to process sensory information. Yeah.
Okay.
Yeah, exactly. Yeah. So as I was saying before, the field was dominated for decades by logical reasoning. Machine learning didn't really have a role. But then slowly the subfield known as machine learning became very, very dominant. I will tell you a little bit about the story behind that, to the point that nowadays, I would say 90% of the field of AI in one form or another deals with machine learning. So that, of course, might create some confusion, because some people outside the field might think that machine learning is equal to AI and vice versa. This is not correct. There are things that we still do in AI which are not necessarily related with machine learning. But nowadays, machine learning is doing it's playing a very, very fundamental role, and actually it's dominating our field. What is machine learning? Well, machine learning means the development of algorithms that improve their performance over time. So usually these algorithms are exposed to data, and to a large amount of data. And during the so-called learning process, the system improves its performance, right? Now, we have to also make a distinction between machine learning and deep learning, because probably most of you have heard deep learning several times on the news, and maybe this distinction is not clear. Deep learning is a specific algorithm or specific class of algorithms within machine learning. It's not equal to machine learning. There are many other machine learning algorithms which have nothing to do with deep learning. For those of you who are a little bit familiar with the field, I can mention support vector machines, kernel methods, also decision forests. There are many, many others. Deep learning is a specific class of algorithms. They are substantial, they are inspired by the structure of the brain. They fall into the category of neural networks. They are called deep for reasons that we're going to see in a moment, because usually this structure consists of a number of layers, a very large number of layers. And so in some sense, they are deep. Okay, I like usually when I teach my classes, my AI classes, I try to give my students a historical perspective to the field, which is always important in my opinion. And so I usually show this little short video, which was done in the 60s, but it's interesting because it already contains all the essential ideas and also problems related to what we do in machine learning nowadays. Now I'm trying to make the video start. Can you hear it? Okay, so the reason why I like this video is, first of all, because, as I said before, it gives the students or the audience some historical perspective, because some people think that AI is a very recent thing, which is not true. We needed decades of research in order to arrive at this point. But also I like this video because there are, as I said before, several things which are very important also for what we do nowadays. For example, the video shows what we do in classification. They were trying to build a system which classifies males against females, and this is a classification problem. Actually, the algorithm that was used in those days was called a perceptron, was a neural network, a very simple neural network, actually, the simplest possible neural network that you can imagine. So we're going to see this later, but now let me show some data which, in some sense, show how dominant is becoming nowadays machine learning in almost every field. Every once in a while, I'm asked by students or friends or colleagues, what are the main application areas of AI and machine learning? Well, it's difficult to list them all, because I find it very difficult to find a single area where in some form or another machine learning or AI is not being used. Even if we are not familiar with that, even if we are not aware of that, indeed machine learning is with us, and it will stay with us. This picture shows the behavior, the number of publications of papers published in the field in the past few years, actually starting from 2007 to 2015. As you can see, there is an exponential growth here. And also, AI is becoming very popular in industry, as you, of course, all of us know. And here you can also see an exponential growth in the revenues done by companies using AI. Now, I want to say something about the very notion of machine learning, because in order to understand how AI works, and I think this is also an opportunity to familiarize ourselves with the basic ideas of AI, it's important also to understand the principles behind that. It's not going to be a technical discussion, but I'm going to show the basic ideas behind that. So, first of all, we need to make a distinction between what we call traditional programming that we teach to our computer science students. Usually in traditional programming, there are three basic ingredients. One is data, second ingredient is program or algorithms, if you want, and third ingredient is output. So usually, if you want to solve a problem, you have to write on your own some algorithm or some program, and then you feed a computer with the program and with some data, and after a while, maybe in a millisecond or so, the computer will give you some response, some output. This is the standard way in which we teach our students. Machine learning allows us to use a completely different paradigm. We're still using those three ingredients, data, output, and program, but in a different way. In particular, we in machine learning, especially in a class of machine learning, we feed the computer with data and the desired output, and we ask the computer to find and to write a program that will give some positive response. So in some sense, we teach the machine how to solve the problem by feeding the computer data. Now, I want to show a very simple example that I use in my classes to show what's going on here. Suppose that you want to, you are working with a company, and your boss asks you to write a program that is able to recognize cats in pictures. You want to build a cat recognizer, okay? So under the traditional approach to problem solving, I mean the computer scientist, has to become an expert of cat recognition. So he or she has to think what is that particular essential feature which makes that object in front of me a cat. not a dog or a car or a computer or whatever. So you have to become an expert. So you start thinking about this problem. Of course, what you see here is an oversimplification. You realize that cats usually have 4 legs. They have, I don't know, 1 tail, 2 eyes. So you write down this kind of knowledge. And then at this point, you formalize this knowledge into a computer program. At that point, you have a program that recognizes cats in pictures. Then you take a picture, you feed that picture to the computer, and the computer will say, there's a cat here, or there's something else. And this is the computer scientist trying to make this program. Now let's try and see how we can solve the very same problem using machine learning. Here, instead of becoming an expert in cat recognition, you just collect a large number of examples. We all know how to recognize cats, right? If you give me a picture with a cat, I will tell you whether there's a cat or not. But if you ask me, why did I make that decision? Why I think there's a cat? This is something that I cannot explain. None of you can do this. So I cannot explain why I recognize that object in front of me as a cat, right? But I can recognize cats. So here is the idea. I just collect a large number of images containing cats, possibly in different shapes, with occlusion, etc., together with other objects that they do not belong to the cat category. And then I have a machine learning algorithm that basically tries to learn how to recognize cats. And this is now the overall situation. This is our computer scientist who is no longer forced to become a cat recognizer expert, but he is an expert now in machine learning. And think how powerful is this approach. Suppose that now we have a program for recognizing cats in pictures, and tomorrow the new problem that we want to solve is to recognize dogs, no longer cats. We have solved the cat recognition problem. And now your boss next day comes to your office and say, look, now our problem is to recognize dogs. Now, under the traditional approach, you now have to become an expert in dog recognition. So you have to start from scratch in some, maybe not from scratch, but sort of. According to this approach, you use the same machine learning algorithm, maybe with some fine tuning, and your only objective would be to collect a large number of examples. So now you see why machine learning is becoming so dominant nowadays, because we can solve a large variety of problems without the need of becoming experts for those problems. And I want to, now going back to cats, I want to mention the story behind the recent success of machine learning. And actually it was a story of cats, dogs, cars, etc. This is a problem that is well known in the field of computer vision. It's called image classification. Image classification is the following problem. I give you a picture like this one, and I ask you, the algorithm, to tell me the category of the dominant object in the picture. So here, for example, we see a cat once again, and I want the algorithm to return a label. There is a cat here, right? If there is a dog, it should tell me whether there is a dog, etc. More or less the same problem we have seen before. Now, first of all, notice one thing. We all see a cat here, a nice cat, but what the computer actually sees is a bunch of numbers, right? Because as we know, pictures are arrays of pixels. Pixels are numbers, maybe a triplet of numbers, and this is what the computer sees. So here you see is a magnification of a small portion of the image. This is what the computer sees, a bunch of numbers. Now, in order to let you understand how difficult the problem is, imagine you are not given that picture, you're given that picture, and you have to tell me whether there is a cat or not. So that's a formidable task, and that's the reason why for decades, people in computer vision have struggled to find a solution. Not to talk about the intrinsic problems related to this problem. You have viewpoint variations. The same object can be captured by different points of view. You might have illumination conditions. You might have scale variations. So in order for us to build a robust algorithm, we need to take care of all these problems, but probably the most formidable problems are on the right-hand side of the slide. There might be non-rigid deformations, for example. We still recognize a cat there, despite the shape is quite strange. And we still recognize a cat in that image, despite the fact that we don't really see a cat. We only see a small portion of a cat. The occlusion here is very severe, and nevertheless, we are able to recognize a cat. So this is a very challenging problem. As I said before, the computer vision community has struggled over this problem for decades. So what happened next? When a few years ago, a group from Stanford decided to build a very large, at the time it was very large, data set containing millions of images downloaded from the internet. And these images were labeled with the correct label. Say, in this image, there's a cat, there's a dog, there's a car, and so on and so forth. And then they challenged the computer vision community. At that point, they said, if you are working in computer vision and you are working on this particular problem, which is called, once again, image classification, for you to publish your paper, you have to test your algorithm over this data set. Otherwise, we don't consider it. So that was really a challenge. And this was a really large scale problem. Oops. Oh, okay, thank you. The data set here contained more than 1.5, almost 1.5 million images, as I said before, downloaded from the internet. And the number of categories, the number of classes was 1,000. So cars, dogs, snakes, elephants, computers, mobile phones, persons, et cetera, et cetera. Okay. It was a very large scale data set. What happened in 2010? After 1 year, this challenge was launched to the community. The best performing algorithm in computer vision achieved a performance, an error rate of about 30%. I'm talking about an error rate. So this means that 1 out of 3 images were mistakenly classified, which was huge error rate. Next year, 2011, a slight improvement to 25.8%. And then 2012, we should remember this date because it is precisely in 2012 that the history of machine learning in some sense has changed. Because in 2012, there was this paper whereby the authors showed how we can use deep neural networks to solve the problem. At the time, deep meant 8 layers of a neural network. 8 layers now makes us smile because now we have hundreds or thousands of layers. But they were able to achieve astonishing results. Look at what happened from 25.8%, the best performing algorithm in the field, we've got 16.4% error rate. So 10% improvement in just 1 year, which was something which we are not typically used to. Usually we see very small improvements. And then next year, by just changing some minor details in the architecture, they were able to achieve 11.7%. And next year, by adding more layer, 7.3. So you can see what happens in the range of a few years. We were able basically to solve the problem. I'm a bit more pessimistic. I usually don't say that we have solved the problem. We have solved the problem on this data set, which is a huge data set. And of course, it's kind of, we have solved the problem, but there are still issues. So I'm a bit more cautious when I talk about these results. To the point that the algorithm was even able to perform better than humans. So some guy tried to see what was the error rate of his own brain, and the error rate was 5.1, worse than the best performing neural network. So here we go, and there we are in the age of deep learning. That was the beginning of the deep learning era, and what we see nowadays, which are basically dominated by AI, machine learning, et cetera, is basically thanks to that work and basically to the research that has been done or that has been motivated by that work. These are, as I said before, these deep learning models are basically neural networks. So these are models that are inspired by the structure of the brain, especially since we are talking about computer vision by the structure of the visual cortex, the part of the brain which is responsible for visual processing. it's a well-known result, which goes back to the 50s, the 60s. This kind of research have given rise to a number of Nobel Prizes. That's especially in the first stages of the visual cortex, the part of the brain responsible to vision, there are a number of layers. We start from the image formed in the retina, and then there's a first layer of processing, then the second one, a third one, and so on and so forth. So the visual cortex is a highly layered structure. And what happens layer after layer? Well, actually, our neurons in our brain, each layer, they extract features. And these features become more and more abstract. In the first layers, these features are very primitive, very, I would say, very crude. Edges, corners, stuff, or some texture. As you proceed in this direction, when you go inside in this deep neural architecture, these neurons are extracting features that are more and more abstract, to the point that some regions of the brain have been found, and some neurons that are able to recognize faces. So they are basically, they respond strongly in the presence of a face or a hand or stuff like that. So that's the basic idea behind deep neural networks. And it's a matter of layers, as I said before, if nowadays we are able to solve very complex problems with these models. Nowadays, as I mentioned before, we have neural networks with hundreds of thousands of layers and which contain billions of parameters. And the learning process is basically becomes a problem of finding these parameters for these neural network architectures. Now, this, of course, also causes some problems. This is a video which shows what happens, quoted unquoted, in the neural network, inside the neural network. It's a visualization which shows how the system works. This is a very simple neural network which recognizes handwritten digits, so 0, 1, 2, 3, up to 9. So the input layer, which you can see over there, is something written by you, maybe, and the system has to recognize whether you have written a 0 or 1, etc. And this is the neural network at work. You can see the activation of these neurons. There are only a few layers, 4 layers, counting also the output layers. And this is what happens inside a neural network. And this, of course, also poses a problem for us and also for all people using neural network. A problem which is called transparency. Transparency means, is our machine learning model, if we open the box, let me put it this way, can we understand what's going on into this box? And the answer is no, and probably you guess why. And this is a problem, because in some real world applications, you really want to know why the neural network provides a certain response. For example, suppose that in your cat recognizer, you feed the network with an image of a cat, and the algorithm provides you the wrong class. It thinks that it's a dog instead. So this is an error, of course, and you want to somehow fix this error. In computer science, we call this debugging. We teach our students how to debug our codes, how to find bugs. Now, debugging here is almost impossible. The poor neural network researcher who is facing this problem doesn't really know what to do with that, because the model is not transparent, right? It's not something that you really can understand. It's a bunch, millions of numbers, and it's almost impossible to understand why the algorithm gave the wrong response, and it's almost impossible, unless you retrain the model, to fix this problem. Pardon? Yeah, I mean, we're talking about neural networks, of course. So what I'm talking nowadays, what we are doing nowadays is using neural networks. And so there are other machine learning algorithms that are more transparent. But this particular class, which turns out to be the most successful one nowadays, has this problem. So if we change algorithm, then maybe we can try and understand what's going on. But the problem is that those algorithms do not work so well as neural networks. So if you are interested in accuracy, nowadays you have to use neural networks, and neural networks come with a problem, right? By the way, I mentioned just one class of machine learning algorithms, which we call supervised learning, which means basically we collect a large number of data, we label the data in the correct way, and we ask the algorithm to solve the problem. We should keep in mind that there are other classes of machine learning algorithms. These are called unsupervised learning, sometimes clustering, or semi-supervised learning, where only a fraction of the data is labeled, or reinforcement learning, where there is an agent which interacts with the environment and gets feedback from the environment. So the algorithm makes a choice, and the environment says, no, look, the choice is wrong, you should have done this way. And this creates a kind of a loop whereby the machine learning algorithm interacts actively with the environment. So here we go. There is I would say, a whole philosophy here behind machine learning. Is a purely data-driven approach to problem solving. There are some people who think that this is going to also create or provoke a revolution, a paradigm shift, also in science, for example. Actually, I want to mention this paper, The End of Theory, which was published a few years ago by Chris Anderson. Not many people actually do agree with his view, but this is a very stimulating point of view. The point made by this paper is that given that we are living in the age of big data, where a large amount of data are available, this probably will have an impact also in the way in which we do science. I mean, classically science, think of physics, has been guided by top-down principles. So Newton, Einstein, or all the heroes in physics, they first invented some model and then they applied it to some data. But here we are talking about purely data-driven approach. So there are some people who think that this data-driven approach will also change the way in which we do science. And the essence of the idea is that data speak by themselves. The data speak by themselves. And now, for those of you who are familiar with philosophy and Western philosophy, this reminds us, and we can consider this as one of the predecessors of machine learning in some sense. This reminds me about the British philosophers, John Locke, David Hume, who among the first advocated the idea that the knowledge that we get from the external world comes only from experience. Nowadays, we say in a different way. We say it comes from data, but it's the same story. So in my view, machine learning today is a continuation of philosophy, of epistemology with other means, as von Clausewitz famously said a few centuries ago. And so we can see machine learning as a radical or computational, I would say, implementation of empiricism, for those of you who are interested in these ideas. Okay, I think that's enough, I would say, for this long preamble, but I wanted to give you some context, because now probably we better understand the ideas behind machine learning AI, but also its limitations, because sometimes we hear on the news things which are not plausible. For those of us who are working in the field, sometimes, there's a kind of an exaggeration about what we are doing. Okay, now I want to focus on the specific application of machine learning and AI on archaeology, and in particular on, I would like to focus on the project that I'm coordinating. It's called REPAIR. REPAIR stands for Reconstructing the Past, Artificial Intelligence and Robotics Meet Cultural Heritage. I'm pretty proud of this acronym because it also contains the very idea about what we are doing. So the acronym itself, the word, tells us what we are doing. We're trying to repairing stuff, right? So this is a European project in the first place, and this is our goal. This is our goal taken from the grant agreement of the project. We aim to develop an AI-based robotic system which will autonomously process, match, and physically assemble large fractured artifacts at a fraction of the time it takes humans to do. And this system is being tested over a few case studies in the Pompeia Archaeological Park. And these are very challenging case studies indeed. I don't know how many of you are familiar with Pompeii. For those of you who are not, here we go. This is a picture of Pompeii. In the background, you will see something a bit intimidating. It's Mount Vesuvius, which, as you probably know, erupted several times, but in particular in 79 AD, and that completely buried the city. And nowadays, this is one of the most famous archaeological parks, not only in Italy but in the world. So actually, for many centuries, people didn't know about that. That was rediscovered the site only in the 16th century, and excavations started then in the middle 18th century. And there are still areas in the Pompeii Archaeological Park which are not excavated. This makes this the old Pompeii, because of course the new town, which is alive and kicking. The old town of Pompeii, one of the most popular archaeological sites in the world. Here are some figures that were given by the people who work in Pompeii. Before COVID, we had to make a distinction before COVID and after COVID. Before COVID, we had in Pompeii about 3 or 4 million visitors per year, which means about 10,000 visitors per day. Of course, after COVID, the situation was for a couple of years has been much worse. But I've been told that nowadays, after 4 years of COVID, now we got back to those numbers even higher. We're going to focus. Oh, here is a picture which I like. You see this little house, this is a picture that we took in 2018 when we started thinking about this project with other colleagues. And so we were thinking about how can we apply our ideas to some concrete case studies. So we got in touch with the director of the Pompeii Archaeological Park, and we went there in 2018, and we showed him our idea. We basically told him what we wanted to do with this project. And the director got really excited. He said, look, we have thousands of fragments coming from several frescoes. We are just stored in storerooms. We try to kind of reconstruct them to some extent, but it's hopeless. So if you guys are able to do something on this, that would be great. And so they took us into this little building, which is now our headquarters. It's our lab in Pompeii. And what we found there in 2018 was basically this. I'm pretty sure that the archaeologists in this room are very familiar with this kind of thing. So thousands and thousands of pieces coming from fresco that was destroyed, by the way, not only during the eruption of the Mount Vesuvius, but also during the Second World War. Pompeii and the region around Naples were also bombed heavily. And so it was destroyed twice in some sense, after the eruption and also after the bombing in the Second World War. And that's basically one of 2 studies. We are working on that those particular fragments. These are fragments of frescoes coming from what they call the house of the painters at work. It used to be a little room where painters could practice, basically. And it's a small building, a small room in a much larger area, which is called the Insula of the Chaste Lovers, which is very well known among scholars. And the second case study is, this is something that happened in 2010. Probably some of you have heard about this. In 2010, a building collapsed. It was a big scandal because it collapsed due to bad maintenance. And this is something that went on the news in the world and was a kind of a shame for us. And so we are trying also to reconstruct portion of the frescoes that we heard there. This comes from the so-called Scola Armaturale. Okay, now let's talk a little bit about the structure of the repair project. There are 3 main parts in our pipeline. The first part deals with the data acquisition and the 3D modeling. So basically what we have to do here is to acquire all the images of all the fragments and to build 3D models for all these fragments. And then it comes the most difficult part. That's the reason why it's bigger. I mean, the box is bigger, because then we have to solve a puzzle. We have to solve a very difficult jigsaw puzzle. Much more difficult than the jigsaw puzzle we are familiar with. for several reasons. First of all, there is no picture on the box here, right? These are frescoes that, you know, they go back 2,000 years ago. Nobody knows how they look like. So we don't have what we call ground truth in the first place. Secondly, these fragments, of course, do not match exactly. Very rarely they match exactly. They are deteriorated. There are lots of missing pieces, of course. There's also an additional difficulty here, which is here we have fragments coming from different frescoes, not just one, because when the building collapsed, of course, there were frescoes on the four walls, also in the ceilings. And it's like you buy 5 or 4 or 5 boxes of jigsaw puzzles, you mix all the pieces together, and then you have to solve these 5 puzzles at the same time. It's a very challenging problem. Not to talk about the sheer number of fragments. We're talking about 10,000, more than 10,000 fragments, a very large scale problem. Well, once the puzzle has been solved, then we instruct the robot to physically reassemble it. And then it comes the motion planning part. So now I'm going to describe a little bit all these stages. I'm going to start with the data acquisition part. And so here is the problem. We are building a data set, which at the end of the project will become publicly available of all these fragments. And for all these fragments, we are building a 3D model. So from home, you can watch, you can study all these fragments, you can magnify pictures, you can rotate it, you can see how they look like. So the data acquisition setup, of course, in order for us to build this setting, we had to consider a number of requirements, a number of constraints. First of all, it has to be cheap, of course, because the project, I didn't mention this, we got 3.5 million euros for dealing with this project. We are a number of partners, of course. The project will end around the end of 2025. But of course, in order for us to build a system which works in also other contexts, it has to be cheap, transportable, it has to be versatile, of course, but also, and this is a problem for us, it has to be non-destructive. We don't want to destroy these fragments, of course. So usually there are 2 approaches here when it comes to 3D modeling of objects. One is 3D scanning, and typically structured light scanners. What happens here, there's a picture which shows what's going on. There is a scanner which projects some light on the object. Here you go. And there are 2 cameras. You can see there, here. There's a camera here and the camera here. And when these patterns of light are projected on the object, those 2 cameras are able to recognize the difference from the 2 different points of view. And this allows the algorithm to physically reconstruct the object. What is the problem with this? Well, this is the scanner, by the way, that we are using. It's kind of cheap. It costs something like maybe 20,000 or 10,000 euros. It's portable, which is important. The problem is that it's very good as far as the 3D modeling is concerned. I mean, it provides us with a good rendering, 3D rendering of the piece. But in solving the puzzle, we also need to have high quality texture and pictorial information on the top of the piece, because it's not just about matching pieces using shape. We also want to match pieces using color. And the quality of these scans are pretty bad. I mean, not as good as we wish. So that's the reason why we also use a second approach in computer vision, which is called photogrammetry, which we can see this here. We take a normal camera. This is not a scanner. And we take pictures of the objects from different point of view. We put the object over a rotary table. The table rotates. And then the camera gets a number of views from that object. And then there are very powerful algorithms which are able to reconstruct the 3D structure of the object. Now, usually in terms of 3D shape, these are poorer than the scanner, that what we get from the scanner. But in terms of quality of the images, they are much, much nicer. So our problem was to have 3D models which at the same time were good in terms of shape, 3D shape, but also in terms of quality of images. And so what we did was to combine those two approaches. This is the pipeline that you can see. There is a scanning platform, the RGB camera, and then we devised an algorithm which is able to merge those two 3 models into a single one. In this way, we have very accurate visual pictures and also very accurate 3D models. Of course, as far as the puzzle solving is concerned, we also need to know the back part of the piece. And so we also scan the back part, and then we have to combine the scannings obtaining from the top part and the scanning obtaining from the bottom part. And this shows the final result over here. This is something that you might get access to once the database will be released. So of course, there are a lot of processing of these fragments. We need to understand what is the flat part, what is the back part, what is the side part in order to solve the puzzle. And here is a video which shows how the algorithm works. Given a fragment like that one, the algorithm splits the object into 3 parts, top, bottom, and side. And that's, of course, important when it comes to the puzzle solving part. Okay, now I want to discuss the most challenging part of our project, which is the puzzle solving problem. And this is a really challenging one. Actually, historically speaking, the interest in computer science around automatic jigsaw puzzle solving goes back to the 60s. It's actually one of the probably the first paper on this subject by Herbert Freeman and Leo Gardner. In this paper, which was published in 1964, if I remember well, this is the first computer algorithm for solving a jigsaw puzzle. And now, since those years, there have been a lot of work in the area. But an interesting phenomenon appears here. In the first place, the first papers, those written in the 60s, really dealt with unrestricted puzzles. And then for some reason, people started focusing more on TOEI commercial puzzles like these ones. And then interest was centered around more simpler versions of the problem, which means square jigsaw puzzles, where of course the only thing that matters is color or not shape. And only recently there has been an attempt to apply these techniques to the real world, to archaeological puzzles. But usually these algorithms work on a small scale, so they are able to solve small scale puzzles. Why one of our problems, of course, is to deal with the thousands and thousands of pieces. So here, for example, this is an example of an algorithm written by my colleagues, which shows how we solve the 10,000 on the left, also 10,000 on the right, and the 3,000 puzzle only using color those. So this is a very simplified version of the problem that we are facing, because these are all square pieces, right? And these are all small pieces. We are not using shape. We are only using colors, right? But the problem that we are facing right now is much more difficult. This is another algorithm which, on a much smaller scale, allows us to solve problems involving both shape and color. You see, these are the pieces of a very small puzzle, and we see how the algorithm dynamically solves it by taking into account shape and color. And at the end of the day, on this small example, it's able to solve it. But the problem is that we are not dealing with these very nice lab-based examples. We are dealing with this kind of things. And all these algorithms, I mean, the algorithms that already exist do not work. So we are developing our own version of puzzle solver, which tries to capture all the difficulties behind this difficult problem. And in doing this, we are using a lot of clues. So far, I've been talking mainly about two clues. The clues that we use when we solve TOEIC puzzles, shape and color, right? When we solve our jigsaw puzzles, we use shape and color. That's it, because it's a TOEIC example. But here, shape and color, sometimes it's useful, very often is not. Because of the deterioration of the fragments, shape sometimes or very often is useless. And color, because of the deterioration of the pigments and on the pictorial part, color also is not so useful. So we need also to find other clues, more powerful. And this is what we are trying to do. In the first stage of our project, we had a lot of meetings with archaeologists trying to understand how they solved the problem. They were trying to understand what are the tricks or the skills. And of course, we learned some things already we knew. We learned a lot of stuff, a lot of new ideas. This is a list of the clues that we are going to use in order that will be incorporated, by the way, into our algorithm. But now we are focusing on something which I would like to discuss very quickly. And this, I like this idea because this allows us to use a principled approach to our problem. It's not just an ad hoc approach, which works only on that particular example. And this brings me to something which it's very important for our story. Something that's happened in the beginning or the first half of the 20th century. There was a school of psychologists who introduced a new approach to visual perception. This school was called Gestalt School because the central concept in their approach was the notion of Gestalt. Gestalt is a German word which is difficult to translate. Maybe a very bad translation would be pattern, but it's not really a good translation. The father of Gestalt psychology is Max Wertheimer. Other famous scholars are Kafka and Köhler. They were working mainly in Germany, but then they emigrated in the States during the Second World War, and they worked there for many years. This is a sentence that we find in the original paper written by Max Wertheimer already in the beginning of this movement. The fundamental formula, he says, of Gestalt theory might be expressed in this way. There are wholes, the behavior of which is not determined by that of their individual elements, but where the part processes are themselves determined by the intrinsic nature of the whole. So the whole, in some sense, comes before the parts. Not only the whole is more than the sum of the parts, which is something that we are already familiar with, but in some sense, the whole comes before the parts themselves. And, every day, every moment, although we are not aware of this, we use these principles. We see patterns or gestalt everywhere, in every moment. Even now that you are watching at me, and now I'm watching at you, we see patterns everywhere, even where there are no patterns. We see constellations in the skies, but there are just dots for us. Oh, we see deers in the sky, but of course, not to talk about visual illusions. These are famous visual illusions. Maybe you see a white triangle there, but there's no white triangle. And here you might see a curved line, but there is no curved line. So we see patterns everywhere, and Gestalt theory, the Gestalt movement that I was referring to, tried to provide principled responses to these phenomena. Much the same way as physics studies the physical world, they said we should use laws of visual perception. So they came up with the laws of perceptual grouping, and I'm going to mention some of them that are the most popular ones. Here you see a bunch of dots, right? And here, for example, if I ask you what you see here, probably you say, well, I just see 6 dots. The space between the dots is the same. But what happens if you just move some dots on the left or on the right, like here? Now, probably if I ask you what you see here, maybe you might say, I see 3 groups of dots, each of which contains 2 dots. So what we're doing is grouping. Those of you working in machine learning, this is clustering, right? And here we are grouping using proximity, but we can also group using similarity. For example, here, some dots are white, some dots are black. And if I ask you to describe those dots, you would probably say, I see 3 groups, right? And so on and so forth. This not only works on dots, but also on curves. Here are a bunch of curves, and probably here we see 3 sets of curves. This is one, this is another one, and this is another one. They are parallel. So parallel curves or lines play a role here, not to talk about symmetry, right? So in some sense, these are laws, in much the same way as we speak about laws of physics. But there is one principle which is very important for the story that I'm telling, which is the so-called principle of good continuation, which says that if you have a stimulus like this, which you might interpret in several different ways, and if I ask you to describe that stimulus, probably you will say something like this. I see 2 curves, a green curve and a black one. But think a little bit about that. This is only one possible interpretation. Another interpretation could be this one, right? So for some reason, our brain, our visual cortex makes a choice. Among a number of different interpretations, our brain chooses one, according to this law of good continuation that Gestalt theorists wanted to formalize. Here we see good continuation at work on our case study. Here are a bunch of pieces taken from the original frescoes in Pompeii. Here, shape doesn't play a major role, possibly color to some extent, but I'm pretty sure that all of you in this room and also from home can see that we are able to solve these little puzzles using the principle of good continuation, because there are lines and curves on these fragments, and using this good continuation approach, we are able to put together all these things, although shape here is kind of useless. Now, I'm going to describe how we are trying to solve this problem in a principled way, and in particular, using the tools that come from game theory or the theory of games. This is a very important area of applied mathematics, which was established in the 20s by von Neumann. Von Neumann here was one of the most famous physicists and mathematicians of the 20th century. The other person is Harold Kuhn. Game theory deals with situations where there are a number of players or agents, if you want, that have to play a certain game. And the question is, how should these players behave in order to get the most profitable situation for themselves? Now, the ideas goes back to the 20s. Then von Neumann published a very important book in the 40s, Theory of Games and Economic Behavior. John Nash, Nash became famous because of a movie. I think the title was A Beautiful Mind, that's right. But John Nash is the one who also established a very important concept in game theory, which is the notion of a Nash equilibrium that we are using in our project. I'm gonna give you an example. Of course, I don't want to bore you with technical details. I'm gonna give you an example of what it means, this Nash equilibrium concept. Now, this is a game that we are all familiar with, right? I'm not sure. Here we go. Rock, scissors, paper. We have all played with that, right? There are 2 players. There are 3 possible strategies. We call them rock, scissors, and paper. And at the same time, 2 players have to show their strategy, and they either win or lose according to a certain rule. So rock beats scissors, scissors beat paper, paper beats rock. Now we can formalize this game, like we have played several times when we were kids, using 2 matrices. There are 2 players, the blue player and the red player, and there are 2 payoff matrices. You see here these numbers, 0, 1, -1. Those blue numbers refer to the payoffs associated to the blue player, and these red numbers are the players associated with the red player. So how should we interpret these numbers? For example, this. If I play scissors, I'm the blue player, and you play rock. Yeah, you pay me, I have to pay you $1, say $1 or 1 Egyptian pound, and you get 1 Egyptian pound. Dollar, you prefer, or euros maybe. Okay. Now, let's see how we can possibly solve this game. And this allows us to introduce this notion of a Nash equilibrium. Now, we're given a more abstract game with two players, player one and player two, the blue player and the red player. Player one can choose as only one among four possible actions: top, high, low, and bottom. Okay? We don't assign any meaning to these. And player two, just three possible strategies: left, middle, and right. Now, these payoffs that you see here, they basically explain how the game should work. And now the question is, what strategy should I use? Should I, suppose I'm player one, should I play top or high or low? The problem is that I don't know, because you are going to choose something and I don't know what you're going to choose, and vice versa. That's kind of a symmetric problem. But suppose that an oracle tells me that you are going to play left. So then it's simple. I just look at the column here, and I look for the maximum number, the largest number among the blue numbers. And the largest number corresponds to bottom. So if I play left, if you play left, I should play bottom. If you choose middle, then I should play low. If you choose right, I should play low. That allows me to get the largest payoff, right? Of course, you are in the same situation as mine. So if you know that I'm playing top, then you will have to choose the largest number in the row. So this means that you have to choose middle, and so on and so forth. Now, at the end of this story, you notice that there is a configuration of strategies here. Yeah, low and middle, which basically got two circles. Now, this is a Nash equilibrium. Formally speaking, this is a Nash equilibrium. A Nash equilibrium is a situation with a configuration of strategies such that no player has an incentive to deviate from that. Now, as abstract as this concept might be, we are using this concept in our project to solve large-scale puzzles. Here we go. In our game, the players are the fragments, the strategies are the positions on the plane, and the payoffs correspond to compatibility. And then the Nash equilibrium becomes a solution of our puzzle. This is an example of how this algorithm works in some simple images. And by the way, this is the original puzzle. One of them is the correct solution, and the other one is the solution provided by our algorithm. They are indistinguishable. And this is how the algorithm works on a small scale example of our archaeological fragments. These are a few fragments taken from the Pompeia case study. This is the solution of an algorithm which was published a couple of years ago, 3 years ago, which is one of the best around, but it failed miserably here because shape and color, they are not useful here, right? While we are using our good continuation principle, and actually on this small scale version of the problem, we solve it. Now, of course, everything is much more complex because we are not dealing with a few pieces. We are dealing with thousands of pieces. Okay, this is a video which shows this reconstruction. Let me go here. We are talking about thousands and thousands of pieces, so it's not so simple as I'm describing right now. And so we devised, we are developing a hierarchical algorithm for solving the puzzle. There are several steps. In the first place, we have to detect key fragments that there are, in some sense, most important. Think of what we do when we solve a puzzle. We identify corners, for example, or pieces belonging to the border. And these are kind of key pieces that we use. So we identify key fragments. Then we detect a group of neighbors. And then we solve those small scale puzzles, maybe consisting of a few hundred pieces. And then once we solve that small scale puzzle, we create a larger meta fragment. And we go back, and in this way, we're going to solve this problem. Now, there is a lot of room for human intervention. Actually, one of the things that we are experimenting right now is how can archaeologists or experts in general can interact with the systems. And there are several ways where this can be done. Before we start the algorithm, for example, selecting the key fragments, or telling us the initial probable position of the fragments, or during the evolution of the process. At some point, the algorithm stops and asks the expert whether the solution found is reasonable or not, or after, maybe after the puzzle solving, the expert might intervene and can tell us that certain pieces are wrong and can give us feedback. This is a short video which shows a very, very clear version of this human interaction. So I'm going to skip some other stuff, and now I want to focus on the last part in the remaining minutes. This is, now it comes the final part, which means the physical reconstruction of the puzzle. One problem we had to face since the beginning of the story was that we have to manipulate these fragments that are very fragile, and we should not destroy them, right? And we are using then a technology which was developed by Robótica, which is called software technology. These are hands, raw hands, not very strong. You can see we have stuff, but at the same time, they're very delicate. They don't destroy these objects. And thanks to this technology, we are able to describe some examples about this. Without destroying them. See that see the pieces. That's time that like that through. Let's do grasp the pieces that when it doesn't fall, it's not a problem. It falls, it goes into pieces. And this is the rest of the graphic part. The development is allowed to learn the position. We have developed an algorithm to deal with the system also uses machine learning for the power. And here we go, this is the platform that we're using. And a few weeks ago, we had a meeting in one of our partners' location in Genoa. And that's the video that I'm showing you right now. It's the version of the very first one. This is the platform that we are using. Without the piece, that's the right now. This is our website. If you want to learn more about our project, and of course, shukran and obrigado. Thank you very much for your attention.
Okay, thank you, Marcello. Now we will have the chance to have some questions being addressed from through Zoom or even here on the room. Anyone wants to address a question? You want it? This is our student. He was trying to address a question and interrupt you. You want to address a question? No? No.
Okay. Thank you.
Obrigado. Now, from home, okay, we have Marcia Villarigues from the School of Science and Technology. Please go ahead, Marcia.
Okay, thank you very much. I work in the conservation restoration. Can you hear me? Okay, I wait.
Okay.
Can you hear me?
Okay. Yeah.
Can you hear me now? Okay, thank you. I work in conservation restoration, and now in Portugal and Nova, we are responsible for a big 3D scanning project. And I was wondering if you are also testing some new equipments, 3D scanners that already have better resolutions, or at least better textures achievements. And one thing that is, it comes from your work. So you are using AI for a very specific issue, that is to put all this together. But how do you see how AI can manage the use of this amount of data? Because all this, each fragment is an amount, it's a data for study, for other studies. So how is this being considered in the project or in parallel projects, maybe at Pompeia?
So going, whether I should use the microphone or not?
Yeah.
Okay, so as far as the first question is concerned, I mean, I know that there are around a lot of scanners with high resolution, but they are very expensive. So as I said at the beginning, one of our constraints was to use portable devices, portable scanners, cheap scanners possible, because of course now we are working in Pompeia, but hopefully our technology will be exported to other countries. So for us, make much sense to use equipments that are very expensive, non-portable and stuff like that. That's the reason why we combine photogrammetry for getting a high quality texture and cheap scanning process. As far as the second question is concerned, well, we are using AI in almost all stages in our pipeline. In the acquisition processing, we are using learning. We are using deep learning for getting 3D models. We are using mastering, and we are using pattern recognition models for solving puzzles. We are using AI learning the right trajectory of the robot of the hand to capture the pieces and to calibrate forces. Because, as I said before, one problem which is not obvious for those who work in this area is that not only the robot has to calculate the right trajectory to approach a piece, but it has to grasp it the right way, because we don't want the fragment to fall in this motion. And this requires a lot of AI, a lot of machine learning. Reinforcement learning, that's right. Reinforcement learning, which I mentioned before. This is the stuff that our colleagues from Medway from this one are doing. Yeah. I don't know whether I responded to the question, but
yeah, thank you.
Thank you. Yeah. You want to mention?
I have some related to the specification of what is you show a data set of images and a graph with the error that was made by the algorithms, and we have been improving. And at a certain point, you mentioned that, well, at least we solved the problem for this specific data set. It is a huge data set with, I remember,
1.4 million
images,
about
more or less. The problem is solved for this specific data set.